Okay, hello everyone. Let's get started. So welcome to today's Adams webinar titled Engineering Lighter and Faster Industrial Robots by Performing Dynamic Analysis. My name is Yijun Fan and I'm the Product Marketing Manager for Adams at MSC Software. There will be a Q&A session at the end of today's webinar, so if you have any questions, please type them down in the Q&A window or the chat window. We will try to have them answered during the Q&A session or after the webinar. So here's the agenda for today's presentation. We're going to mainly talk about the industrial robots and how Adams can basically help you address some of the engineering challenges when you're designing industrial robots or any kind of industrial machinery or machine tools with similar mechanisms. We will have a few case studies following some general slides, and then we will have a demonstration of basically we're going to show you how you can analyze how the gear rattle effect is going to change the trajectory of your robotic arm. Okay, so first, what is an industrial robot? So as the general topic of robot, Adams has really a lot of applications in that area. And the most famous one, I believe you all have heard of, is the Curiosity rover landing sequence. I think you have all seen the YouTube movie called The 7 Minutes of Terror. So basically, the NASA JPL, they were not able to test most of those tasks on Earth. So as a matter of fact, they have to rely on a simulation tool like Adams to help them basically predict all those physical performance of this Curiosity rover during the landing sequence, including how they want to set the control algorithm to make sure that the rope would break at a certain time so that they can ensure the success landing of the Curiosity rover. So that was a $2 billion project, and I think that was probably the most expensive project involving designing or making sure a robot is functioning properly. So in that specific use case, we can see that they can actually leverage Adams together with co-simulating together with a control software they design either in like MATLAB or any other control algorithms to actually evaluate whether or not they would work in the real physical scenario. So today's topic is more specific on the industrial robot. So what is an industrial robot? Industrial robot is a robot that's performing the predefined activities in the manufacturing process. So usually we say there are, we would categorize that as two different types of manufacturing processes. The first type of process is to basically be picking or placing products, which does not involve things like a lot of the manufacturing process itself. But nowadays, the industrial robot manufacturers, a lot of them are also trying to customize their industrial robots so they can perform some of the basically machining process like the laser cutting, like laser welding, or the metal forming. So those kind of metal cutting or machining process would also be one of the future applications for the industrial robots. So those are the two types of different scenarios we're going to be covering today. The reason why industrial robots is becoming a increasing market, or it's becoming a hot topic among the industries, is that, of course, we know if you're talking about a task where it involves a lot of handling different objects or different parts, the robot has its speed, strength, and accuracy force endurance, that is definitely going to give him a lot of advantages over, human labor. And also to reduce a lot of like repetitive work in the manufacturing plants, like in automotive manufacturing plants, or especially as a growing market, the electronics, like the smartphones, the electronics manufacturing plants, to basically take over those repetitive work would free the workers to do more of the more complex and more intellectual tasks. So that's another advantage of using the industrial robots. A third advantage is that nowadays the robot can really be flexible and be customized to do different tasks and avoid any kind of standstill times. So those are some of the reasons industrial robots is being applied more widely nowadays. And of course, there are some very typical engineering challenges for designing an industrial robots. Of course, the first and most foremost, everyone wants to increase the operating speed of their machine. But increasing the operating speed might generate some other problems, like you might need to apply a higher force on your, you might either choose a larger motor, you want to apply higher force on a lot of your components, so that might cause some of the parts to deform a little bit more than you want it to. Or if you want to increase the operating speed for a lot of the machining industrial robots, you might generate some, so the interaction between the tool and the workpiece is very fierce, and that can generate some excessive vibration. So there are a lot of performance-related issues that is going to contribute to the final precision of your industrial robots or machinery. So those are the kind of things you need to take into account when you try to increase the speed of your robot. And of course, you want to try to validate your control algorithm so that you want to make sure the control logic will take into account, basically it will capture some of the physical facts, like was the gear rattle going to affect your final trajectory, or how the deformed part is going to be contributing to maybe some of the accuracy for your final, processing, cutting, or machining process. So those are all kinds of things you want to take into account when you are trying to increase your speed or lightweighting your product. If you want to lightweight your product, you change the stiffness and the system natural frequency. And as a result, you might have some resonance effect because your system natural frequency is very close to your operating frequency. And also, when you try to lightweight your product, a lot of times you will end up having a more flexible part than the original design, which can also cause excessive vibration. So those are the engineering challenges that can be generated when you are trying to optimize your industrial robots. And today we're going to talk about basically how you can leverage atoms to help you address those engineering problems. So the first big topic is to basically increase the operating speed while maintaining the precise positioning. Like we mentioned before, usually higher forces have to be applied if you want to increase the motor speed, and you want to probably have a larger motor. Another way is to lightweight your mechanism itself. So with the same amount of torque or force applied on a lighter object, you will end up having you will basically be able to have a higher acceleration capability for your different robotic arms or other components of your system. So those are basically two different types of methods that can help you increase the speed of your robot. And of course, you can also achieve that by optimizing your robot arm moving trajectory. Maybe moving from a different route or different path will increase the efficiency of your entire, operation speed. So when you want to increase the force, when you are applying a higher force on some of the components, the fact is that you will get higher loads, and as a matter of fact, you will get some of your components will get a little bit larger deformation than the original design. So in this case, being able to capture that deformation during your modeling or simulation process is very critical to precise prediction of your moving trajectory. So also you want to take into account, you want to basically capture some of the effects like the gear rattle effects. So the gear backlash or the bearing clearance, how that is going to change your the moving trajectory of your object. And we're going to cover that topic of the gear rattle effect during our demonstration today. So first, for the flexible body integration in the robotics, there are different ways in Atoms you can basically do that. You can either have so you can basically incorporate the linear flexibility or what we call the nonlinear flexibility. So if the deformation of an arm, for example, is not very big, not very large, you can use Atoms Flex to basically create a model neutral file to capture some of the small deformation of that component during the operation or during a task. And if you want to include the nonlinear flexibility, for example, you have some very large deformation at some components, then you can also do that by some of the nonlinear flexibility capabilities of Atoms. By leveraging that, you can also achieve both small and large deformation. And those will sometimes be very important to calculate the robot arm trajectory. So our flexible body integration method can work with some of the major FEA codes like MSC Nastran, MARC, Abacus, or ANSYS. So if you are using those FEA software as your simulation tool, that can be coupled with Atoms to help you increase the accuracy of your dynamic model. Next is the gear rattle prediction. We have this tool called the Atoms machinery, and with that you will be able to create those gear systems with very high efficiency. And as a result of creating those gear systems using Atoms machinery, you will get the actual contact between the different gear teeth. So, for example, you will be able to set the angle of the backlash for the two gears in one gear pair. So you will be able to capture those kind of rattle effects as a result. And how that rattle effect is going to change, your moving path of your final object. We will talk more about that in today's demonstration. Next is the design study, DOE, and optimization. To optimize your trajectory, you might want to observe several parameters like the length of a certain object, or you want to really define the contact between the two different parts. You want to set the contact parameters correctly. So there are different variables that can basically contribute to the final optimization object. And so as a first step, you want to do a design study to find out what are the variables that are most sensitive to the final goal. And then after you have found out some of the more sensitive variables, you want to perform a design of experiment to basically look for several peaks that can actually result in the maximum value or the minimum value of your study or of your simulation. And after that, you want to perform the optimization analysis around those peak points. So all those can be achieved using Adam's and Adam's insight. So that is something you want to do for a lot of your robot design. Like you want to really see if you want to move your robot from this path or from another trajectory. You want to change the motion, or you want to change the torque or forces applied on your motors to see how that will affect your final movement or final path. That can all be achieved by through Adam's insight. Next, validating the control algorithms. So defining the controller strategy is very essential to your machine design. In the video here on the bottom, you can see there's it's actually from a YouTube video called the Timo Boll. He's a very famous ping pong player in Germany. So him versus the KUKA robot. So I don't know how, is that a real competition or not, but to even film a video like that, you need to have a very precision, control of your robot to achieve those kind of movements during a competition with a real, table tennis champion, world champion. And that is why the control algorithm is very important to perform different tasks. So there are a few things you want to take into, you want to consider when you are validating the control algorithm. Of course, you can always design and evaluate your control logic in your control software like MATLAB, Simulink. But if you really want to validate that with the real physical effects, like how you want to see the contact between the different parts is going to affect your final trajectory, or basically how the structural deformation is going to affect that. So to evaluate your control algorithm with those real physical scenarios taken into consideration, you would need basically to have a co-simulation between Adams and your control software to help you very accurately validate if this control algorithm is going to work or not. And also, if you are designing a control algorithm, you are not going to put into motions. Instead, you are going to control the force or torques of your motor that's driving your machine. So force and torques is something that you want to definitely evaluate with a closed-loop control system. And also how the robot is going to accelerate and brake at certain instant or a certain point. All those kind of stuff can be monitored and can be simulated with this co-simulation between your dynamic solution and your preferred control environment. So in this scenario, you can see with Adams, you will be able to co-simulate with not only like MATLAB or EZ5, but any of the software that supports the FMI standard. You will basically be able to study how the interaction between the control systems and the mechanical systems is going to affect your final physical performance of your product. And in this case, you can see that there are several electric motors that's driving each, I would say, axis of this machine tool. And with these electric motors are also created within with using Adams machinery motor module. And with that, you will actually be able to select one of the options as the external control logic. So you will be able to use the control algorithms you define in the MATLAB and import that into this motor system, and using that to drive your system and see how this works in your real physical test scenario. Okay, the next important topic is how to reduce the vibration. So as we all know, vibration can be generated through two different type of scenarios. First, if you try to lightweight your robot, as we mentioned before, it changes the stiffness and also the system natural frequency. So what you want to do is to verify that the operating frequency really stays away from the system natural frequency to avoid any kind of a resonance effect. And also, sometimes when you try to, we work with a lot of customers, sometimes they try to lightweight or they try to reduce the mass of some of their components. And with that component, with the mass of that component reduced, they will often observe a lot of the fact that a lot of parts are more flexible than they used to be, which can cause a lot of vibration than they didn't thought of in the first place, basically. So those are the two basic reasons why lightweighting can cause some excessive vibration. And also, for another source of vibration can be generated if you are using your robot to do some kind of a machining work. So in like metal forming or laser cutting, for those kind of products, very strong interaction exists between the tool and the workpiece. And if you try to like increase the speed of your tooling or machining process, that will also cause excessive heat and vibration, and which will definitely affect your system performance and also the precision of your machine. So how can we address those problems using atoms? So first, using atoms vibration, you will basically be able to calculate the system natural frequency under different and also you will be able to evaluate whether or not there's a resonance between your system natural frequency and maybe some of the operating frequency of some of the components or subsystems inside your product. And also you will be able to evaluate results from a frequency domain. There's a we have a fast Fourier transfer that will enable you to basically convert your time domain results into the frequency domain results directly from the Adams post-processor. And that will also help you analyze some of the, you will be able to find out the frequency of your under different operating scenarios and analyze the data from the image perspective. So a lot of our customers also use Adams vibration. They were able to drastically reduce the machine vibration, those vibration can be generated by either increasing the operating speed or from lightweighting the product. But you will always be able to accurately predict the vibration from your system, and you can choose to either increase the stiffness of some of the components, or you can choose a different moving path of your robot arm trajectory to help you evaluate how to reduce those kind of vibration issues. So for the industrial robots that's used for machining or manufacturing, as we mentioned before, another factor that you want to consider is the interaction between the tool and the workpiece itself. So in this scenario, we recommend a new solution called the Atom Smart Co-Simulation, as a lot of you have probably heard of before. So we have this new technology where we are enabling our Atoms users to run co-simulation with our nonlinear FEA solution called the MARC. So on the video on the left-hand side, you can see that we are actually, it's a metal forming robot. So you will be actually be able to evaluate not only the robot system itself, how that moves and how that vibrates, but also you will be able to capture the large deformation of the workpiece and how the interaction between the workpiece and the tool is going to affect, you know, the transmissions or the gearbox, how that is going to affect the robot itself, how that's going to cause the varying forces or the changing torques for the system. So that is something very interesting for us to you know, observe. And also for some of the machining processes like the laser cutting or like grinding process, we also enable you to perform a coupled thermal and mechanical analysis in this co-simulation. So you will actually be able to see how the heat that's generated through this machining process will maybe potentially affect your system performance. And those are some of the what we call the new technology that you can really look into for if you have similar, you know, design requirements. So here is some of the companies out there that are leveraging atoms in their design and study, and also research development process. And also we have some. So 24 out of the top 25 automotive manufacturers are using atoms. We have all the big aerospace customers, including like some of the famous industrial robot companies like the FANUC and ABB. So they are all using atoms at some of the research centers around the world. So next, let's go through some of the case studies we have. So the first case study we see is the work from a university called the ETS from Canada. It's a work out from Dr. Youssef. So what he did here is that he basically innovatively designed a what we call the cable-driven 6DOF loading simulator or loading robot that can be used to apply any desired forces and torques on the target objects. So in this scenario, he's applying the torque and forces on an industrial robot. So the final goal is to basically help test the stiffness of the industrial robot by you know, applying torques and forces and observe the deformation of the robot itself. And in this scenario, he used atoms to create a basically a virtual physical prototype for this robot, as well as the target robot, which is the industrial industrial robot. So what he did here is that he simulated the required tension in the cables that he used to drive or to apply loads on the objects. And so he was able to basically use the atoms and MATLAB co-simulation to optimize the control logic for this loading simulator, and to apply the minimal force or torque needed in order to apply the target load on the target object. And as a matter of fact, he achieved good correlation between the physical results and the simulation regarding the target robot stiffness. So he calculated that using the simulation that's done by the Adams model, and also they did a physical test which shows that the stiffness that's calculated by the simulation and the physical test achieved very good correlation. And also he was able to save cost by very accurately simulating the tension in a cable instead of building multiple physical prototypes and use force. So they would actually use the force sensors to monitor the force in the cable. So reducing the number of physical prototypes and physical tests will drastically save the cost and time for the projects. So that is what they achieved by Adams simulation. The next case study is from a famous industrial robot manufacturer called the ABB. So what they did is that they built the Adams model for their industrial robots and evaluated the simulation of their industrial robots under different types of operating scenarios. So with this method, they were able to basically confirm that some of the customized configuration would actually work for a lot of different operating scenarios before they even build the first prototype. So they were able to verify that this configuration or this customization is actually working. In this way, they would be, this enables basically them to make their R&D process much more flexible, to help accommodate the flexibility or the demand for customization in the nowadays manufacturing process. And the third case study we are going to take a look is a sort of a folding robot, or we call it packaging folding robot. It's from Dr. Ferdinando from Italian Institute of Technology. What he did here is that he used Adams to study a tucking operation. So this operation might seem not too difficult if you want to, for you to do that tucking movement, it might be very easy, but it's not that straightforward for a robot to do the same kind of achieve some kind of operation using the certain mechanism. So they were actually able to really test how this mechanism would work and evaluate how different folding methods, and it compared the pros and cons of different operating scenarios for their different mechanisms of the folding packaging machinery before they built their first prototype. So as a result, they were able to achieve high accuracy or a very good correlation between the physical test and the simulation on both robot displacement and the contact force between the carton and the robot finger itself. So they will also included flexibility into the Adams model, like we talked about before. They included the flexibility into some of the parts that can potentially undergo some deformation or larger deformation than the other more stiff components. So in this way, they will be getting a higher accuracy from their simulation when they're trying to predict the very complex robot behavior. So those are the techniques that we mentioned before and are actually very effective in a real-world simulation. Okay, next let's take a look at a demonstration. Okay, now let me stop sharing the presentation and let's go to the Adams environment. This is a demo model that we created for as a conceptual industrial machinery. So here, in this particular model, this robot will pick up the object and place it on another table. So let's first take a look at the simulation results. So in the simulation results, you will actually able to see there's a function called the trace marker. So with that function activated, you will be able to observe the trajectory, exact trajectory, moving trajectory of that object. So let's take a look. I hope you can see the animation through this WebEx here. This entire robot is driven by several pairs of gear systems. So we have a few planetary gear systems, we have a few bevel gear pairs, and then we have some spur gears and helical gears. So we did a comparison with different gear rattle effects, basically. So with those gear pairs created in additive machinery, you will actually be able to change the kind of gear backlash angle that you want for those different gear pairs. So we did two simulations, the one with two gear pairs having some certain level of gear backlash. Another simulation is with the system going without any kind of backlash in any of the gear pairs. And then we actually compared the results for both simulations, and we actually observed some differences in the movement or in the XYZ displacement for this final object, which I will show you later in the post-processor. So when this robot is picking up the object, you can actually see the real trajectory, what we call the tracing, the mark tracer here at the white line, kind of a white line. So that will move along with the object, or any point, or any basically, if you want to observe the moving trajectory of your robot arm on a certain point, you can also do that. Any specific point within your system, you can observe how it moves and what the path is for that particular component or the final object. And you can, after you observe the real trajectory of your system, you can change the motion or change the control algorithms to see if you can have a better trajectory, the better final trajectory for your object, for your target object. Or you can see actually how, if you make some of the parts flexible, how that is going to change, or how that's going to affect the accuracy for your final movement. And in this particular scenario, you will also be able to see. Let me show you how we basically change those backlash effects. So in this gear system, we will just click modify. So this is a bevel gear that is placed currently at the bottom of the industrial robot. So that is the bevel gear that we're talking about here. So the bevel gear, through this wizard approach, you can choose different kind of fidelities you want. But even with the simplified method, you will be able to define the backlash angle, or what is the kind of parameters you want to set in the backlash, and define that in your gear pairs. And if you don't want any backlash, you can just set that value to 0. So, and in the post-processor, let me go to the post-processor real quick. So in the post-processor, you will also be what you can do is that you can observe the X, Y, and Z axis of displacement for your moving object. So for example, while you are moving this object, what is the difference between the trajectory with the backlash and without the backlash. And you can see with the gear means with backlash here in this case. So the red curve is the one with the backlash. You can see actually, you can observe a lot of vibration, the back and forth vibration caused by the gear rattle effect that will actually be affecting the final movement. So it's not a big deal if you are just moving or placing that object. It's probably not as a big deal with picking the object as you would, as it would if you are actually manufacturing or if you are machining that object. If you are really trying to perform some of the milling or like laser cutting, so those will actually be more influential or more detrimental compared to this picking up or placing different products. But if it's going to affect the final position of your object, then it's going to be a problem of your design. So that's something you want to observe and avoid during your design process. So that applies also if you want to observe how the flexible, making some of the parts flexible, how the deformation of some components. You will also be able to study how that is going to change the displacement of your final object or the tool of your manufacturing robot. Okay, so that is the demonstration that we want to show you. So as a summary, so with atoms, leveraging atoms, you can increase the operating speed while maintaining the precise precision of your industrial robot. You will be able to validate the control algorithm by atoms and a control integration. You will also be able to reduce the excessive vibration caused by either reduced weight or the machining process. And that will be the end of today's presentation. Okay, let's go to the Q&A session. So if you have any questions, please type them down in the Q&A window or the chat window. And if you have some more detailed questions that you want to ask, you can send an email to this address.